Okay, so we're going to continue with section 3.7. We did some the other day, so a little bit more here today. We're going to start with a problem that involves the Pythagorean theorem. That'll be problem number 24. Let me put that up on the board here for you. So, a little boating problem. They've got a nice little diagram here for us. It says a boat is pulled into a dock by means of a winch 12 feet above the deck of the boat. The winch pulls in rope at a rate of 4 feet per second. Determine the speed of the boat when there is 13 feet of rope out. What happens to the speed of the boat as it gets closer to the dock? Okay, so we're just going to do part A here. And let me kind of zoom out a little bit and give you my artist rendering of the boat. So let's see. There we go. 12 feet here above the dock. 13 feet here. And then draw your best rendering of the boat right here if you like. Label it the HMS Jeff Parent or the HMS Calculus, whatever works for you. Let's call this side X, this side Y, and this side Z. And let's see what kind of things that the problem tells us. It says the winch pulls in the rope at a rate of 4 feet per second. Well, is there a way I can characterize that? 4 feet per second. So the winch pulls in the rope. So here's your boat. Here's the top of the deck. Here's where you have the winch. So it's this side that's getting pulled in. How can I characterize that it's getting pulled in at a rate of 4 feet per second? Nice. Negative. What else here? What's negative 4 feet per second? Let's not deal with distance and rate and time, that kind of thing. Let's deal with calculus. What calculus expression can I use to denote how that's changing? There you go, dz dt. Nice, dz dt is 4 feet per second. Let's see, what else do I know? Well, I know this side and this side. Do I know anything else? Or can I figure out anything else? The answer to both questions is yes. First of all, is there a way I can figure out what x equals? Yeah, Pythagorean theorem. With a right angle here, this problem should be screaming out Pythagorean theorem. So it does. Let's see what we can do with that. Well, I think this is a Pythagorean triple. 13 squared equals, yeah, it's going to be 5. I mean, this is a standard Pythagorean triple. 169 minus 144 equals x squared. X equals 5. So we've got x, y, and z. 5, 12, and 13. What am I looking for? I'm looking to find what happens to the, let's see, to determine the speed of the boat when there's 13 feet of rope out. What happens to the speed of the boat as it gets closer to the dock? Call it constant rate. Oh, here, let me put up the problem here so you can take a look at it too. We're going to be looking for a rate here. Determine the speed of the boat when there's 13 feet of rope out. So how fast is it being pulled in? In other words, this side right here. How fast is it moving? How would you characterize that in terms of the variables that we have written out here? Perfect. dx by dt. That's our unknown. But as far as this problem is concerned, right now we don't have anything to plug into. There's no equations. We need an equation to plug into. So in order to get an equation we can plug into, we're going to have to differentiate something. We're going to have to differentiate it implicitly. Any idea what we can do to start? What equation can I differentiate implicitly? Perfect. X squared plus y squared equals z squared. So let's start by finding d by dx, it's going to be d by dt of this. D by dt of that. What's the one thing you have to keep in mind when you're doing related rates problems? When you differentiate here, you have to do so implicitly. All of these are functions of time. All of them are functions of t. So when you differentiate, you have to use the chain rule. What's the derivative of the first one? Good. 2x dx by dt. And then so on. After that, 2y dy by dt. And 2z dz by dt. So you're applying the chain rule as you differentiate each of these. Derivative of the outside, that's just like a regular polynomial term. Take the exponent down, subtract 1 from the exponent, times the derivative of the inside. Since you're differentiating with respect to t, you don't get a 1 here, you get a dx by dt. You can, if you want, take time to divide out the 2. I'm not sure that it's really all that worth it all the time or not. It doesn't hurt. Maybe it's not a bad idea. Let's see what we know and see what we don't know. Well, there's one more unknown here that I haven't accounted for, and that is my dy by dt. So what can I put in for dy by dt? Well, let's think about what that is. That's how high the deck of the boat is, or it's how high the top of the deck is from above the top of the deck of the boat. It's this distance. So what could I put for dy by dt? 0. Good job. Why 0? Yeah, this height isn't changing. The distance that the winch is above the deck of the boat isn't changing. It's staying the same. And if it's not changing, then its change with respect to time is 0. So let's put that in here. X is 5 times dx by dt, which is negative 4, plus y, which is 12 times 0, equals negative 4 times dz by dt. Oops, you know what? I think something's wrong. Dx by dt is, oh, I got these backwards. Let's try this again. 5 times dx by dt plus 12 times 0 equals 13 times, where is it? dz by dt is negative 4. So 13 times negative 4. Yes, sir.
Why isn't it 5 times 2 times dx dt?
I divided out the 2.
Oh, right. Okay, yeah, I see that.
Okay, so that's 5 dx by dt equals negative 52. Dx by dt equals negative 52 over 5, or about negative, actually not about, exactly negative 10.2. No, 10.4. What units would go with this? Let me go back to that in a second. What units go with this? Feet per second. All right, it's going to be a rate. In this case, it's feet per second. Let's see here. All right, as far as dy by dt is concerned, dy by dt reflects the change in this distance. but that distance is fixed. The height of the top of the winch above the height of the deck of the boat is fixed. So there's no change. If there's no change, its rate of change is 0. It's a constant. So its rate of change is 0. That's why dy by dt was 0. Yeah, so we're talking about the rate of change with respect to time. So in this case, this is the rate of change of the position of the boat with respect to time. So in this case, it's a negative 10.4. Now, sometimes I'll remind students ahead of time, sometimes I don't, about the negative. But Dom caught that early, that there needed to be a negative here. What's the interpretation of that negative once we get down to here? Once you get down to, the dx by dt is negative 10.4 feet per second. What's that mean? The boat's coming closer, all right? And that makes sense. The derivative being negative reflects the fact that that length is shrinking. It's getting smaller, as it should. As you're reeling this in this direction, that distance is going to get smaller. So the fact that it's negative makes a lot of sense. In fact, we're happy to see that there. Yeah, that's really moving pretty good. 10, yeah. Yeah, yeah, this is true. I didn't exactly draw this to scale, but yeah, you're right. Yeah, it's somebody's gonna be taking the boat to the repair shop because they're not gonna stop it in time. Yeah, I don't think so. In fact, I know that they're not. There's one problem in my algebra book where they have like five regular baseball mitts and one catcher's mitt costs like $130. I'm like, you could spend that much on a catcher's mitt alone and it'd be cheap. Yeah, it's pretty funny. Yeah, I don't think that they're really thinking about realism at all when they do these things. All right, the important part though is that it's a good first example of a Pythagorean theorem problem. We're going to do one more here. Is there any thoughts on this one before we move on to the next one? Doing all right there? dz by dt would be the rate of change with respect to time of this side. And that rate of change is how fast you're reeling in the rope. So that was given to you as a negative 4 feet per second. That's how fast this is. That's really cranking in the rope pretty fast too. So again, perhaps not well thought out in this sense, but a good example of a related rates problem dealing with the Pythagorean theorem. Okay, so let's move down to problem number 28. And let's see if this one is any more realistic than the previous one. So in problem 28, let me kind of sketch it out here for us. We've got somebody running some bases. Now, I'm not going to make you be a baseball guru. You don't have to remember that there's 90 feet per side here. That's fine. I'll cover you in that sense. I would give you this information. And I'd probably go even further and label this one first, second, third, and home, just to be really safe. Yeah. Well, no, there was somebody, I won't mention name or gender, this morning that, had somebody going from third to home on this problem. Yeah. Oh, yeah, safe. Yeah. All right. Yeah, I missed that one. Sorry. Good on you. All right, so let's take a look at the problem here real quick. It says, for the baseball diamond in exercise 27, suppose the player running from first to second base at a speed of 25 feet per second. Find the rate at which the distance from home plate is changing when the player is 20 feet from second base. So let's draw that. You're 20 feet from second base. So call it here. And we want to know how this distance is changing here. Let's see about labeling some things and figuring out some things. It's reasonable to assume that that's a right angle. In fact, it is. And let's label some sides. What do you want to call the length of this side? X, all right. Y. And Z. I'm just messing with you. Z, right? Across the pond, they call it Z. Also, if you ever listen to some people from England, if you listen to them talk, they don't talk about math. They talk about maths. It's plural. Mathematics is not singular. It's plural. Maths. Yeah, it drives me crazy. I'm like, ooh. They don't know how to say aluminum either. It's aluminium for that. But that's a different story. I'm not trying to pick a fight with our friends across the pond here. Let's do some calculus. So, all right. Can you see what's headed our way? What can I just start with? Let's just do it right away. Pythagorean theorem. X squared plus y squared equals z squared. And let's see what we know. We're given, for instance, that x is 90 feet. We know that. Ooh. We actually do kind of know what y is, right? Because the whole side here is 90 feet. But he's 20 feet from second base. So what's the length of y then? 70 feet. So that means 90 squared plus 70 squared, 8,100 plus 4,900, that's 13,000. So this should be this. Let's just call this the square root of 13,000 feet, right? Pythagorean theorem, right? 70 or 90 squared plus 70 squared. 90 squared is 8,100 plus 4,900, 13,000. Take the square root on both sides. Okay. Now, let's see what else we know. We're going to need, actually we're given something here. It says the player is running from first base to second base at a speed of 25 feet per second. How could I characterize that? 25, but what's equal to 25? What can I write is equal to 25? dy by dt. Good. So dy by dt equals 25 feet per second. Good question. If y was this distance, then it would be decreasing. But y is the distance from first base to second base, or to where the runner is. So would that be negative or positive? Yeah, it's going to be positive in this case. dx by dt and dz by dt. We get another one for free out of this. Which one do we know and which one do we have to find? All right, we don't know what this one is, but we do know what dx by dt is. I want you to think about dx by dt, write it down on your paper, and then compare it with a neighbor. See if you guys can come up with the same answer. And if not, then educate each other. But figure out what dx by dt is. So figure out what dx by dt is. Chat each other up. Come on, I want to see. So here's your chance to interact with a fellow human being. Talk to somebody other than Siri. Habibi, what's... No? Shlonik, all right. What'd you get? Yeah, okay. All right. All right. So how is this rate changing? Well, what is dx dt? It's the distance from home to first, and that distance is fixed, right? It's just 90. That's it. So if that distance is fixed, what's its rate of change? 0. So dx by dt is 0. All right, back up here to differentiate. Again, differentiate with respect to t, d by dt. Regard all of these as functions of t and use the chain rule. Derivative of the outside times the derivative of the inside. So 2x dx by dt plus 2y dy by dt equals 2z dz by dt. As before, you can divide out the 2 if you want to take the time to do that. That's fine. Not a bad idea. But there's 6 different terms in this equation. We know 5 of them. So we can solve for the remaining unknown. In fact, at this point, when you substitute in, it becomes a linear equation, really. All right, so I'm going to substitute into the equation after I delete all the 2's. So let's say goodbye to the 2's. Let's divide them all out. Hasta la vista, sayonara, ciao. There we go. So I'll be left with 90 times 0 plus 70 times 25 equals square root of 13,000 times dz by dt. All right. So very obligingly, part of that term drops out. This part right here, that's just 0. So let's think. 7 times 25 is going to be what? 1750? Divide by the square root here. And we get 1750 over the square root of 13,000 equals dz by dt. Very important here. What units go with this? Feet per second. So you're talking about how fast this distance is changing. Feet per second. That's it. That's my job. Yeah, you can leave it like that. I mean, if I want a numerical value, fine. If not, no big deal. So, but yeah, that's fine. And I'm not really worried about the fact that, you could rationalize the denominator or factor out a square root of 100, whatever. That's just arithmetic stuff, all right? We're worried about the calculus. So is there any questions on the calculus part of this stuff? This one? The Pythagorean theorem? We used the Pythagorean theorem to figure out what z was equal to. I didn't actually show that work, but if you do carry out that work, it's 90 squared plus 70 squared equals z squared. So 8100 plus 4900 equals z squared. 13,000 equals z squared, so z is going to be the positive square root of that. There is a negative square root, but we're not going to use that for length. We use that formula because in differentiating with this with respect to time, we've got a relationship amongst all these rates of change and the lengths of the sides. So it gave us an equation we could plug into in order to finish solving for the rate of change with respect to time of this side. Yes, sir. Yeah, I should really, ideally, I should write it right next to this, but I didn't leave myself room. But it's in feet per second. Well, it's the whole thing. It's so 1750 over square root of 13,000 feet per second. So just regard this as one number. Let's actually find a decimal value for that. You got me curious here. 15.3 sounds good. 1750. Nah, should be more than that. Oh, 15.3 feet per second. That's moving pretty good. That's about 10 miles an hour, I think. You know, that's not too bad. Yeah, yeah, I think it's well, it's Miguel Cabrera trying to steal second. He's just not really fast there. All right. Okay. Are we all right with this one? All right. All right. Appreciate the questions there at the end. Let's try problem number 30. All right, so we've got a man walking to a light post. The man in problem 30 is 6 feet tall. He's walking at a rate of 5 feet per second. How fast is the length of his shadow changing? Okay, well, let's find out. Let me kind of draw this in a very abstract way. So we'll draw a triangle involving the telephone pole and the tip of the guy's shadow right here. And then we have a gentleman which is 6 feet tall. There's my gentleman, an amazing stick figure here. Rembrandt, eat your heart out. The light is 20 feet tall. The man is 6 feet tall. Do we know the length of his shadow? No. No. So we'll call that X. And I'm not sure, did they tell us the distance between him and the light pole? Yeah, so when he's 10 feet from the base of the light, at what rate is the tip of his shadow changing? So let's call this distance S. And you might be able to solve this with a Pythagorean theorem, but I guess what I see more than the Pythagorean theorem on this one is something we saw the other day. Does anyone else kind of see what I'm heading towards? Similar triangles, yeah. You've got the triangle here that I'm highlighting in yellow. And then I'll follow that up with a smaller triangle, a similar triangle. And I'd highlight it in green, but my green marker has been usurped by board gremlins. So let's go with a very manly pink. So these two triangles are similar triangles. Can we characterize anything that we know right now? What are some of the pieces of information that we know? All right, nice. So the ratio of this side to this side, 20 over s plus x equals 6 over x. Perfect. So just using the fact that these are similar triangles here. Is there any information that we know? Something that the problem told us, maybe a rate in there? Like how fast he's walking towards the light pole? All right, he's walking towards the light at 5 feet per second. So how would you characterize that? D what? ds by dt. And you're spot on with the negatives. Good job. It's negative 5 feet per second. Why is it negative? It's walking towards it, so that distance is shrinking. It's getting smaller. That's why it's got a negative value. It wasn't negative in the baseball thing because that distance here was increasing. As he's running towards second, dy by dt is getting bigger. Yeah, but it's the length of this side. It's not necessarily the triangle itself, but it's the length of that side is getting longer. In this case, if you're walking towards the base of the light, then ds by dt is getting smaller. Okay, let's work with this a little bit before we try and find something that relates to dx by dt. dx by dt, by the way, is the remaining unknown variable here. So if I cross multiply, then I'll get 20x equals 6 times s plus x, or better yet, 20x equals 6s plus 6x. Suggestions here. Yeah, I'd subtract 6x from both sides, right? 14x equals 6s. All right, that's all well and good. Any other suggestions here? Something very important that you have to do. It's part of all of your related rates problems. Well, we're not really going to have to get rid of one of the variables here. Somebody said it. Differentiate. In fact, you have to differentiate implicitly here, right? So you could divide both sides by 14 first if you wanted to. It's not really going to make a difference. We're still going to get the same derivative, but we want to calculate d by dt of both sides. I think in my morning class I solved for x first. That's all right. What do I get when I differentiate this entire equation? 14 dx by dt equals 6 ds by dt. Well, let's solve for dx by dt. dx by dt equals 6 over 14 ds by dt. Or I could simplify that to 3/7, bless you, times negative 5. Oops. ds over dt. Dx. What units go with this? Feet per second. Remember, these are always going to be rates. Your dx by dt, etc. There are always going to be some rates, so it's going to be something per unit of time. Yeah, yeah.
So when you found the ratio of the similar triangles, you put 20 over the entire.
Yeah, so the length of this side over the length of this side, because it's, yeah, I'm dealing with the entire larger triangle, right? And then for this ratio, so let's kind of color coordinate them. That ratio comes from our big triangle. And then this ratio comes from the small triangle. So it's still the height over the base. And it was the height over the base in the larger triangle. So we're doing the exact same thing for both triangles. There's two other hands. Yes, sir.
What exactly is x?
X is the length of the shadow, right? Because the guy's walking towards this. He's casting a shadow. It's X units long.
Oh, okay.
You can actually figure out how long X is, but you know what? We don't need to. So.
All right. I thought it was the like the distance, like from the initial distance to like the where he is.
Okay.
So I thought it was 5, but I get it.
All right. Good. There's one more? No? Okay. Maybe I answered it. So, good. Let's see here. We got some time here. Let's move on to another problem unless you have some further thoughts or comments on this one. All right. Go ahead. Fire away. In order to get an equation that involves a ds dt or dx dt, you're going to have to differentiate something. All right. So we had an equation. I could have differentiated it here, but I played with it and I made it simpler. What would be the problem or difficulty differentiating with respect to x, say right here? Quotient rule. Ugh. No, thank you. In fact, in our next problem, we're going to take a little bit of pain to avoid the quotient rule. All right? But, yeah, I could have used the quotient rule here, you know, even here. But, boy, I've been playing with the equation a little bit. I got something that was much, much friendlier to differentiate. Okay? Yep. Yep, we're finding how fast is the length of the shadow, which we characterize with x, how fast is that changing? So that's your dx by dt. Oops, other way. Okay, does everyone have a calculator today? If not, you will need one. Not only for the current problem, but for section 3.8. Thank you. Thank you. Thank you. Okay. Thanks. We're going to look at problem number 39. There's a couple challenges that this problem presents us. One of which is calculating the derivative, and the other one is actually just plugging these expressions into your calculator. So let's practice on both of them. On an exam, I would not give you something quite so number intense to work with. I mean, I really want to, it's like, who comes up with this stuff, right? Really. I mean, these are pretty impressive numbers. 4,347 over 400 million. Okay, that sounds pretty precise. And then this exponent here is pretty crazy too. Let me start by copying that down, or actually letting you copy that down. How about if we both copy that down? I have no idea. I do know that they came out a couple years ago with revised wind chill factor tables, and the original wind chill factor tables, I know that they had some volunteers, exposing their skin to this obscene conditions and go, okay, it feels really really cold, and they're actually giving you a number. Yes, sir.
Yeah, I saw stuff like that, and it's like numbers to like the 1000s place, and it's really like it depends on so much stuff. Like,
Yeah.
what kind of clothes you're wearing, you can't get it to the 1000s place. It's really rough.
Yeah, it is. It's a very rough estimate.
You don't know like were they wearing a t-shirt or a jacket or what? Like,
Yeah. Oh, he'd be a hurting pup for sure. All right, I was having problems with the zoom on this. I think I've learned to fix around it. There we go. That's a little bit better. No, I don't want it back here. No. All right, we'll save this one till later. Sorry, Dave. No, I don't. All right, I'm hearing it on my microphone. It's going to be kind of funny for somebody to listen to this to on YouTube. All right, problem 39. Let me write down the formula here. H. I'm going to call it H of capital T. And the reason I'm using capital T is because the T that they use represents temperature. But I want to use my little t for time. So H of capital T is 4,347 divided by 400 million. That's a 4 followed by 8 zeros. E to the 369,444 power over 50 times capital T plus a mere 19,793. You just can't make this stuff up. So, one challenge that we're going to face is simply finding the value of this, and this represents the relative humidity at a couple different temperatures. So let me help you put those into your calculator. Just to put this expression into your calculator is probably worth partial credit right there. All right. I'll tell you what. I'm feeling your pain. So I will clear out my expressions and I will do it with you all over again, even though I had this done. So I would strongly recommend that those of you who have MathPrint hit the alpha key and then the y equals key. And that allows you to type in a fraction kind of like the way we like our fractions, a numerator and a denominator. The numerator is 4,347 divided by a 4 and then 8 zeros.
how'd you get the fraction over fraction again?
You hit the alpha key and then the y equals key. The first thing you'll see on that menu will be your answer over fraction. If you don't have that option, if you got an older calculator, an older 84, the 84s can be upgraded. You can upgrade their operating systems to do that. Next, I want e to some power. And again, it's probably nice if I do that answer to fraction, or that fraction trick again. So hit the alpha key, then the y equals key. Again, let's select number 1. Just press enter and type in 369,444 in the numerator. Hit the down arrow to go into the denominator. 50. We're going to have to use an x here, unlike the t that we have over here. 50x plus 19793. Yeah. So, kind of a challenging expression to put in here, but I think we got it. If you don't have that fancy capability, then what you're going to have to do is use parentheses. So I could do that in the first part by just dividing. I hope I got 8 of them. Dividing that fraction, leaving in a parenthesis. The second part, e to some power. Again, I need parentheses. 369,444 divided by parenthesis 50x plus 19793, right parenthesis. So it's not as easy. It can be done. The reason I had you put it here is so that we can evaluate this at two different values for T. We want to find the relative humidity at, I think it's like 65 degrees or something like that. Yeah, 65 and 80. So this is assuming that the dew point is itself 65. Now let's just check one setting here. Hit the second key, then the table set. Make sure your table set is like this, with the independent set to ask. So that's second and window. Make sure independent is set to ask. If it's not, cursor down there, put the cursor on ask for independent and press enter. With that adjusted, hit the second key, then the graph key, and that'll take you to the table. And then if there's anything there, you can delete it. Just type in the values we want. We want 65, and we want 80. So the relative humidity at 65 degrees is almost 100%. The air would be pretty saturated with water. If you went out for a jog, you'd be sweating buckets. If it was 80 degrees, there's, the humidity's gone down. It's only 60%. So how are we doing? Are you able to match my numbers that I have here up on the board? Error. Error. If you got errors, come on up. Let me take a look at your calculators. Oh, that's because you don't have a 4 here. You need a 4 there.
Probably when I was inserting the parentheses. Did I put two parentheses?
I don't know. We'll find out. Error. You still have an error here. Delete there. Boy. Oh, you need a parenthesis around the left-hand side of this. Yeah, you're gonna have to go back and practice this a little bit. Left parenthesis there. Delete. Now let's try. Still an error. Probably should have just started from the beginning here.
Would it be quicker to show error examples on the screen?
Yeah.
Same error, possibly, or different errors? Which one?
Let me try. Let me see this here. Let me see what some of these other ones are looking like. All right. What you're missing is a parenthesis around the denominator. So. All right. So let's do 65. Yeah, that's good. Same thing. You're missing a parenthesis around the denominator here. You need another one around the numerator too. So there, and then one here. Yeah, that works. Oh, let's see. Table. Table set. Oh, it's because you don't have a function program yet. It's not there. Oh my. You got this big parenthesis here. I don't know what you did to do that.
Then after,
I don't think we need it.
but even without it, there is.
Oh, well, it's because you got, all right. You're raising this fraction to that exponent. You don't want that. So, all right. I would do it this way. Let me exit that. Second here, and then use the numerator denominator. Alpha, and then y equals. So it's like 4347 divided by 40 million. All right, and then next to it, you do your e. All right, but again, alpha, and then the y equals. So give that a try.
Kind of E, right? This one right there. It's okay.
Okay, delete. Okay. All right, let me just take a look at this. No, it's not. Okay. I haven't figured out what's wrong with hers yet. 4,000 E. Oh, well, this number is different. Should be, we got an extra 4 in there. Now let's try it. Okay. Thank you. Yeah, that's up to speed. Okay. So we calculated a couple of values. H of 65 should give you something in the 99%. So H of 65 is about 99.791. H of 80 was 60.201, etc. So, Alex, you want to get the door there? Thanks. Okay. Now the challenging part of this is going to be to try and find the derivative. Let me be very clear about something. In finding the derivative, it's going to be kind of tricky, and we're going to have to work with a lot of big numbers. I would not give you something this number intense to deal with on an exam. It's just a little bit too involved. Yes, sir. You just plugged in two different values. One you plug in 65, the other one you plug in 80. So you should be able to match those in your table function. All right. But the parts of this that you need are good practice in terms of differentiating. It's good practice with the chain rule. It's good practice in thinking about how you can avoid the quotient rule. So in that sense, it's worth going over. All right. Dom smiled when I said avoid the quotient rule. 2 thumbs up. Cool. Let's work on the derivative. We're going to differentiate this with respect to little t. Big T is temperature, little t is time. All right, so we'll call it dH by dt equals. Now let's think about this as far as the derivative is concerned. In fact, let me over here maybe remind ourselves of something. If I differentiate with respect to x, e to the u, what's the rule? What's e to the u times the derivative of u. Now the book might write it as u prime, and that's fine. But it's e to the u times the derivative of u. Basically, it's the function times the derivative of its exponent. Let's keep that in mind as we do the derivative here. What's the easy part of this derivative? We get a constant here, right? Constant. So you just ignore the constant. It's just going to be 4347 over 400 million. And then the function, okay, so, and let me do this with the function. it's just going to be e to this power, right? Times the derivative of this power. But how about if I rewrite this a little bit? Because if I leave it as it is, when I differentiate that exponent, what rule do I have to use? The quotient rule. Let me write it as 369,444 times 50t plus 19,793 to the negative first power. So now, I mean, this and this are the same. Really, all I've done is change that. But in differentiating, I've got to multiply by the derivative of that exponent. So I need a little more room. Let me zoom out. So d by dt of 369,444 50t plus 19,793 to the negative first. So I've got to differentiate that exponent. Then I should be done with the derivative part here. So 4,3, yeah, I know. 4,347 over 400 million e to the, I don't have to write it like this anymore. I've already used this form of it to get the derivative, so let me just write it back like this. 50t plus 19,793. Now, what's the derivative of this term going to be? All right, this is a constant, so that's going to stay there. 369,444. Good, you got to apply the chain rule here. So let's apply the chain rule. You've got this whole thing, which you can think of as your outside function, something to the negative first power. So the derivative of the outside, what comes out in front of this? Negative 1. So times negative 1, 50t plus 19,793 to the negative 2 power. Don't forget we got to subtract 1 from there. Here's where you want to finish this and hit a home run. Don't make just one person do all the work here. What's the derivative of the inside? 50 dt by dt. Remember, you have to differentiate that implicitly, that last little bit here, right here. So when you differentiate that, you're going to get a 50 dt by dt. Capital T is temperature, little t is time. Yeah, that's the inside part. The outside part gave us the minus 1 here to the negative second power. The inside part is right here. Okay. I'm not sure there's a whole lot we can do to clean this up, but let's do a little bit, all right, to make our life a little bit easier. This and the 50 are all up in the numerator. This term is down in the denominator. So let me write, and I'm not going to multiply these out. I'm just going to leave it as is. So it's going to be 4,347 times minus 50. Yeah. So this times this times this. So I still need the 369,444 divided by 400 million. What else am I going to have in the denominator? Well, let's see. Let's just leave this here. E to this power. 50t plus 19793 times what's left. This term, let me put it in the denominator. 1 over 50t plus 19793 squared times dt by dt. So a fair amount of work here to find the expression for dH by dt. The expression for dH by dt is not a lot different than the expression that we started out with for just h of t. And we're going to kind of take advantage of that as far as finishing off this problem. So to finish off this problem, we needed to do two things. I need to plug in a new temperature, because they ask you for the rate of change of the relative humidity when the temperature is 75 and the rate of change of the increase of the temperature, that is dt by dt, is 2. So, wow. So we're going to plug all this in and put in a t equal 2 here as well. Let's see how we can do this with a minimal amount of effort. And that's my goal here, is to finish this off with a minimal amount of effort. If you notice, this and this were all part of our original function, right? So what I want to do is I want to multiply the original function by this and by 2. So if I put in a 2 here, 2 times that's going to be a minus 100. Let's just clean that up a little bit. So when dt by dt equals 2, then I'm going to have 4347. Yes. Thank you. 4347 times a negative 100 times that 369444 number over 400,000, or 400 million, I should say. Three, 6, 9, 4, 4, 4, 50t plus 19793. Okay. So again, I'm going to circle the stuff that we already have in our original function. It's this part and this part. I want to multiply my original function by these extra factors, by this one, and then divide by the square of this one. So there's a shortcut in doing all that, especially given how much of a pain this has been in terms of calculation. It'd be nice to take advantage of some technology to take a shortcut on this. So take out your calculators and go to the y equals key. I want to multiply my original function by these missing terms, by this one, and divide by the square of this one. So, what's that?
2 is the time, right?
2 was the rate of change of temperature with respect to time. Okay. So, on your calculator, with the cursor at y equals 2 or y2, and clear that out, look for the vars. We're going to go back to this later when we do Newton's method, so it's not a bad idea to find this now. If you press the vars button, you should see a menu like this, and we want the y variables. So cursor to the right should give you another menu like this. Press enter. Vars. So right next to the clear key. So press the vars key. Let me get back. Press the vars key. Then go to the arrow, one arrow to the right. That gives you your function. Press enter. And press enter again. Oops, I should have done that in here, that Y2. So vars. There. So now you have Y1. And we can kind of continue to edit with this. So that's this whole expression. Hit the times key, and let's put in the last things that we need. The last things we need would be this. So times, and you can do that any way you want. You can just multiply that out. I'll do it as a fraction. Negative 100 times 369,444 divided by this term squared. So I'll put that in with the x's. 50x, oops, that has to go in the denominator. So parenthesis 50x plus 1. Oh, yeah, I'll take care of that in a second. 19793 parentheses squared. And you're right, I got an extra 5 up here now. All right. Yes, sir.
How do you make it go in fractions? I'm not used to the.
The alpha key right there, and then the y equals key will give you the fraction menu. Just press the first one. Whew. All right. Last but not least, let's go to the table. Second table. We wanted to evaluate this when x was 75, and what you're going to get now for y2 is how the relative humidity is changing as the temperature is increasing. So as the temperature is increasing by 2 degrees per hour, the relative humidity is decreasing by 4.732%. So I'm very happy that that was consistent with the number I got in my morning class. So dH by dt equals negative 4.732. Now, I don't expect you to do all this kind of stuff on an exam. It's showing you a few of the things you can do on a graphing calculator, and it's giving you some ideas as to what you might do to avoid certain calculations. Doing them kind of by punching things in one at a time. Some of the main things you should have got was what we did here to avoid the quotient rule, rewriting this, from here to here. We rewrote that so that we could avoid the quotient rule. We did use the chain rule here. That's another thing that I wanted you to see. Let's use a chain rule, and that gave us our dt by dt here. The calculator stuff, if you picked up something there, great. If not, then hopefully you weren't too bored. Okay. I don't think I'm going to change the homework. So homework is still going to be 1 through 29.